All right, welcome back. Today we're going to talk about 7.6, which is an introduction to exponential functions. In order to talk about an exponential function, we need to know first what it is. So, an exponential function is one that does one of two things. It either starts small and begins to grow slowly at first, then faster and faster. Or an exponential function can start large there we go and decay or get smaller, slow or fast at first, decay quickly first, then slower and slower. All right. So let me kind of draw you a picture of what each of these could represent. So the first one, we talk about a growth. That graph starts small at first and then grows quickly. You can see it grows from something, so it never ever touches this x equals 0 line, or I'm sorry, y equals 0 line, the x-axis. It can never equal 0. If it's a decay, which is the second one, it starts large, it's small quickly, and then slows down. And again, it never touches this x-axis because you always have to have something. It might be super, super small, but you always have to have something that's decaying. All right. So an exponential function has a function rule where the variable or the unknown is in the exponent. So for example, if I have y equals 3 times 2 to the x is in the exponent, so this is an exponential function. Whereas if I had y equals 3 times 2x, x is not in the exponent function, so this is not exponential. This is the difference between the two. Let's try an example. Let's decide if we can figure out how to determine if something is exponential. Alright, so we're going to begin by looking at a table, and we want to determine from this table whether it's exponential function, which will either grow slowly at first and faster, or whether it's a linear function. And I want to remind you, when we have a linear function, this is constant on how it's growing. Or, of course, it would make a line. All right, so let's look at the table we have. In this table, if you look at these numbers, this one grows by 2, it grows by 4, and then it grows by 8. You can tell here that this is not a constant growth. Therefore, this is an exponential function. A better way to tell would be to plot these points. So let's do that. If it were a linear function, it would fall in the line. If it's an exponential function, it does this curve that will increase quickly. So the first point we have is the point 1, 2. So 1 and up 2. 2 and 4. 3 and 8, and 4 and 16. You can see that this does not fall in a straight line. It's this curve. Whoop, not a very good drawing I got going on there. Let's try that again. All right. It's this curve that grows quickly at the end, right? So again, you can see this is an exponential function. How about example number 2? In this one, let's determine if the function, and we're going to look at the rule this time, is exponential. And of course, we're going to explain. All right, so if you're given y equals 3 times 4 to the x, you will notice that the x is in the exponent position. Since the x is in the exponent, or the unknown, the variable, is in the exponent, this is an exponential function. How about this one? Let's say I have y equals 3 minus 4x. This would not be, because the x is not in the exponent. How about one more? How about, let's say, f of x, which again, remember that f of x just means y, equals, how about 1.5 to the x. Again, your variable is in the exponent, so this is yes. And again, for the same reason. Let's try something a little bit different. But example number 3. I'm going to ask you to evaluate the function for the given for the given value. So I'm going to use function notation this time. That's the f of x equals, and let's say 4 to the x, or x equals 2. So what I'd like you to do is take this 2 and you're going to plug it in for x and evaluate it. So this equals 4 to the 2 power. Now why am I not putting 2 here? That's because this is our function notation. This just means y, right? So here if we evaluate, this is 4 to the 2nd power, or in this case, 16. Try another one. What if I said g of t? And again, this just means y, it's function notation, equals 2 times 4 to the t. 4 t equals -3. So we're going to take -3 and plug it in for t. And again, we're plugging it into this one. This is just function notation. So you have equals 2 times 4 to the -3. And again, anytime you plug in something for a variable, you put it in parentheses. Now, we just finished a whole section talking about negative exponents. Where does this move to then? That's going to move that 4 to the denominator, and our exponent will become positive. So we're going to have 2 over 4 times 4 times 4, or 64. And then you'll notice that this fraction does reduce. So our final answer is 1 over 32. Now, yes, you can plug that into your calculator. And again, don't forget, you can hit math or enter. And I'll reduce the fraction for you. That is one option. Gunnar agrees. How exciting. All right. So Gunnar was really excited about how well we did this problem. Now that we understand how to evaluate, let's talk about sketching a couple of these graphs. Let's do example 4. Sketch a graph of the exponential function f of x equals 2 to the x. All right, so anytime we're graphing, there's 5 points that we use every time. What are those 5 points? In our table, we always use -2, -1, 0, 1, and 2. And again, our y is the same as our f of x. That's what it's going to equal. So we're going to start here. We're going to plug in 2 to the -2 power. And again, that negative exponent drops this 2 to the bottom. And we get 1 over 4. Next one, we have 2 to the -1 power. Again, it's going to drop that 2 to the bottom. And our exponent becomes a +1, or we have 1/2. How about 2 to the 0 power? Anything raised to the 0 power is 1. 2 to the first power is just 2, and we have 2 to the second power. So 2 times 2, which equals 4. Let's plot these points, and we'll see if we can graph our exponential function. Remember that we want our exponential function going to approach the x-axis, but never ever cross it, right? So in the first one, we have the point -2, 1/4. So -2 and up 1/4. We have -1, 1/2, up 1/2. We have 0, 1, so 0, 1. We have the point 1, 2, so 1 and up 2. And then we have the point 2, 4, over 2 and up 4. We're going to connect our dots. All right, and again, that curve's going to be very close to our x-axis, but never crossing it. Let's try another one. Same idea. So example 5. Sketch the graph. And let's just make it a little bit tougher this time. How about if we have y equals 4 times 0.5, I'm going to put that in parentheses, to the x. All right, so again in our table, put our table over here, our x values are going to be -2, -1, 0, 1, and 2. We're going to plug these in for our x. So we're going to have 4 times 0.5 to the -2. Well, 0.5 is the same as 1/2. I'm going to write it in that form so we can talk about it a little bit. A negative exponent on a fraction. If you recall in our last lesson, that just flips this fraction over. So this is 4 times 2 to the second power. And 2 times 2 is 4. Times 4 is 16. All right. How about this one? We have 4, and again, I'm going to write that as 1/2 to the -1. If you use your calculator, you can put in a decimal. That's fine. Because when you're plotting it, a decimal works just as well. A negative exponent here is going to flip our fraction over. So we have 4 times 2 to the +1. Or 2 to the 1 is 2, times 4 is 8. How about 4 times 1/2 to the 0? Well, anything raised to the 0 power is 1. So we have 4 times 1, which equals 4. How about 4 times 1/2 to the first? That's 4. 1/2 to the first power is still 1/2. And 4 times 1/2 is 2. And the last one we have here, we have 4 times 1/2 squared. And again, remember, we're going to distribute that square to both parts there. So we have 4 over 1 squared is 1, and 2 squared is 4. 4 times 1/4 equals 1. Let's plot our points and graph and see what happens. All right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 is our biggest number. So we have -2 and up 16. So -2 and up to 16. We have -1, 8. 1, 2, 3, 4, 5, 6, 7, 8. We have 0, 4. 1, 2, 3, 4. We have the point 1, 2, so over 1 and up 2. And of course we have the point 2, 1. So over 2 and up 1. And again, this one starts very large, and then it approaches or gets smaller and smaller. This one is what we call a decay. All right, so why are exponential functions important? Well, we can actually use exponential functions in real life situations. There's many things out there that you can talk about, either grow slowly at first and quicker, or that start really big and then break down. So one thing they always talk about as an exponential function is bacteria, for example. It multiplies and multiplies and multiplies to the point where you might start with just a little and then within moments have a lot. So we're going to actually apply some of this to a real life situation. And you guys always know when I say a real life situation, we're on our way to a wonderful word problem. All right, so some things I want to talk about. Your basic exponential function usually looks like this. Y equals, there's a number in front, we're going to call that A, and then B to the X. This A actually represents our starting amount, how much you're starting with. B is always your, what we call our growth or our decay factor. It's what it's being like the multiple of, or how quickly or how it's growing or decaying, getting smaller. Now, our exponent is what we really want to focus on today. Our exponent actually means the number of times it's going to happen. Let's see, let's make that a T. It happens. All right. So here we go with example 6. You invest $4,000. It'd be great to have $4,000 right now. And that doubles, in value every 5 years. The model f of x equals 4,000. Again, that's that starting amount. It doubles, that's your growth factor, to the x, represents your investment, where x is the number of doubling times. What I want to know is how much is it worth in 25 years? All right. So they give you the function already, right? This function over here, this f of x equals 4,000 times 2 to the x. That's the function we're going to use. And all of your word problems today give you the function. You don't have to write them yourself yet. Don't you love how I put in the word yet? Just like in class. All right. So what we really need to talk about is this exponent. What are we plugging in for x? And remember that x is the number of times it's going to happen. Well, it shows you right here that it doubles in value every 5 years. And we want to know what it's worth in 25 years. So how many times is it going to double? It's going to double 5 times. So we're going to plug in 5 for x, right? If it was only in 10 years, it would double twice. If it was 20 years, it would double 4 times. So in 25 years, it doubles 5 times. All right. So we have 4,000 times 2 to the 5th power. You can grab your calculator, or remember we do order of operations. We're going to do our exponent first, so 2 to the 5th power, or 2 times 2 times 2 times 2 times 2, which is 32. And then we can multiply these, and we find out it's going to be worth $128,000 after 25 years. All right, so all 3 of your word problems today follow the same idea. You need to figure out what your exponent's going to be. You're provided with the function rule. If you have any questions, let me know. Good luck, you guys.